We're going to go over chapter 6, questions and problems, the last 3 pages, and then we'll probably work on the home, I guess, take home test. There are 2 parts actually. I should have put that in one huge page, like one file, but for some reason it was giving me a lot of glitches because of a lot of drawings that was done on the word processor. So I had to split them up into 2 separate files, so I'm sorry. But total of 4 problems, and you should be able to work on that. Open notes, right? You could use your notes. You could use your textbooks. You could use example problems that we did in class, and then finish it by this weekend, end of Sunday, I guess, and then upload it separately in 2 separate categories. All right, I explained that before we start that. All right, so let's take a look at number 26. All right, number 26. Um, it says here you have 2 springs that are identical, except that spring 1 is stiffer than spring 2, which means the K value for spring 1 is greater than K value for spring 2. All right. So, on which spring is more work done if they are stretched using same amount of force? All right. So, if we had 2 springs, right? We have spring A, spring 1, right? And then we have spring 2, okay? Now the K value for spring 1 is definitely greater than K value for spring 2, okay? So when we talk about work done on spring 1 is equal to, right, K 1/2 Kx squared. I mean, it could be negative, but we're just going to be working with just the magnitudes, okay? And work 2, which is for spring 2, is equal to 1/2 K2, right, x2 squared. I guess this is K1 and x1, okay? However, depending on how much force is used onto each of these springs, we're going to stretch this spring at different lengths, right? Obviously, this is going to be less of a pull than this, right? Because if we use same amount of force, the weaker spring will stretch more than the stiffer one, right? So let's find out how much spring will stretch by using force of spring is equal to Kx.
No, I was just looking at how you have your setup, because I'm trying to get something similar set up.
Sorry about the interruption. All right, here we go. So this spring force that you're applying onto spring is exactly the same value. So this Fs and this Fs are the same things. However, this K value are going to be different, right? And the amount of stretch is going to be different. So, like that. So if we were to solve for x, my x1, okay, is equal to F spring over K1. Okay? And my x2 will be same force Fs over K2. So if I were to substitute this x1 into here, what do I get? I get my work 1 is equal to then 1/2 K1 times Fs over K1 quantity squared. That becomes
1/2 times K1 times Fs squared over K1 squared. Notice how the K1s will cancel out, leaving you just K1 at the bottom. So this cancels out with this. So here, get work 1 is equal to 1/2 Fs squared over K1. Similarly, if you were to place this into here, you get your work 2 is equal to 1/2 K2 times Fs over K2 quantity squared. So if you do the same thing, I'm going to get pretty much the same thing as this, except you're going to have K2 at the bottom. Right? So your work 2 is equal to 1/2 times Fs squared over K2. Now, 1/2, they're the same. Force of spring squared is exactly the same value because they're using same amount of force. However, if you're dividing by a bigger number, you're going to get a smaller value for work. If you're dividing it by a small number, you're going to get bigger work than this. So since K1 is bigger, you're going to have smaller work 1 than work 2. Okay, so in this case, your work 1 is definitely less than work 2. For part A. Should have given you more room, huh? But what about part B? They want to know, for part B, if they are stretched the same distance. Now, we have to say, okay, for part B, work 1 is equal to, right, 1/2 K1 times X squared. Now, X is common for spring 1 and spring 2, right? And work 2 is equal to 1/2 K2 X squared. So these x's are the same. K1 is definitely bigger than K2, so 1/2 are the same. So in this case, work 1 has to be bigger than work 2. Okay? All right. Now let's take a look at number 24. Okay? Describe the energy transformations when a child hops around on a pogo stick. People still do that. Well, let's take a look. So here, if you don't know what pogo stick is, it's like a something that you stand on, right? And you grab onto this bar. So a person can, I guess, grab onto this and then stand on this thing. And then there's a spring like that where they could just bounce off of, right? So if this is the ground, let's draw the ground. So if this is the ground, okay, this pogo stick when when the spring is compressed, right, the pogo stick is down here. Now, I'm not gonna like draw a person on it. So let's just, this is the pogo stick. When the spring is compressed like this, only thing I have here is just potential energy of spring, right? And then this potential energy of spring, when the spring is uncompressed, right, and this pogo stick rises like so, right, it has kinetic energy and slight potential energy gravitation because it's going up, right? It gains height. Then, when the pogo stick is at the maximum height, only thing I have is potential energy gravitation. Then, right as it hits the ground, spring hasn't been compressed yet, right? Right as it hits the ground, I have kinetic energy and slight potential energy gravitation, just ever so slight, because this is the height difference, right? The height difference is from here to here. Then, when this thing is compressed, again, the same, right? This height is x, really, right? Same amount that spring compresses. So when this spring is compressed, only thing I have is potential energy of spring. And then cycle repeats itself, okay? It just continues and repeats itself, okay? That's how the energy is transferred from the potential energy of spring to kinetic energy and slight potential energy gravitation to total potential energy gravitation with no kinetic energy when it reaches the maximum height. Then as it falls back down, you have kinetic energy and potential energy gravitation. Then we have total potential energy of spring, no kinetic energy when it comes to a instantaneous stop, okay, and so on, okay. Hope that illustrates what I'm talking about. All right, good. Now let's take a look at number 25. A spring constant, or a spring has spring constant K of 440 newtons, newtons per meter. How much must the spring be stretched in order to store 25 joules of potential energy? Okay, so let's say we have a spring mounted to a wall, and we want to stretch this thing, right? We want to stretch this thing to a certain length so that it gains 25 joules of potential energy. Right? So the distance of stretch that distance x will create 25 joules of potential energy. So potential energy of spring is really equal to 1/2 kx squared. It's that simple. And we want to store 25 joules of potential energy. So 1/2 times 440, which is the k value, x squared. So if I multiply 2 to both sides, I get 50. Divide that by 440. Square root it will be my x. And my x now is equal to, if you do this calculation correctly, I think you'll get something like 0.337 meters as the stretch value. That was pretty simple, right? All right, any questions so far? Alrighty. Next. All right. Number 26. A 75-kilogram trampoline artist jumps vertically upwards from the top of a platform with speed of 5 meters per second. Well, when the trampoline artist jumps to 5 meters per second, on the way back down, when he reaches the same height as he started, he's going to come down at 5 meters per second, right? So if this is our initial condition right here, right, he's going to have, or she's going to have, kinetic energy. And since this trampoline artist has a height, going to have potential energy gravitation as well. Okay? So if I were to sort of like redraw this, so here's the trampoline artist, right? He's going to come down with initial velocity, right? Initial velocity of 5.0 meters per second. So definitely has kinetic energy, right? And then this trampoline is located 3 meters below. So this height right here is 3 meters to the top of the trampoline. But this trampoline has a stretching value, so it sort of has like, it acts like a spring where it stretches to a certain distance before the trampoline artist comes to rest. So here is the amount of stretch, x, from unstretched to stretch. And this trampoline is going to behave like a spring with K value of 52,000 newtons per meter. That's a pretty huge K value. Okay? So this is really our zero right here. This Y final is 0 here. And this is our Y initial. So let's think about the energies that are involved. Initially, here I have potential energy gravitation initial, and I have kinetic energy initial. Here, when the spring is completely stretched out, I have no kinetic energy. I have no potential energy gravitation because my height is 0. I only have potential energy, potential energy spring final is the only energy I have after the spring is stretched out. Okay, so I guess you could draw out the trampoline artist here. Right? So since there's no work done by friction, right? Since work done by friction is equal to 0, we can say total energy initial must equal to total energy final. So initially, I have potential energy gravitation initial plus kinetic energy initial. For final, I have only potential energy of spring final. So mdv GH, right? Or you could say Y initial if you want to, right? Plus 1/2 MV initial squared, right, is equal to 1/2 KX squared. So this is the H right here. So 75 times 9.8 times H, which is 3.0 plus X, plus 1/2 times 75 times 5 squared, is equal to 1/2 times K, which is 52,000 times X squared. So if you work it out, right, this, you have to distribute this. So 75 times 9.8 times 3, right? You get something like 2205, right? Plus 75 times 9.8 times X, you get 735X, plus 1/2 times 75 times 5 squared, right? So what is that? So 25 times 75 times 25, and you get 937.5, okay, is equal to this. So 52,000 times 0.5 is 26,000 X squared. Therefore, this looks like a quadratic equation here, right? So if I bring everything to the one side and set it equal to 0, 0 is equal to, right, 26,000 X squared minus 735X, right? Minus, when I add these two together, what do I get? So 937.5 plus 2205, and I get 3142.5. So you can use quadratic formula here, right? So X is equal to, right, minus B plus or minus square root of, right, B squared minus 4 times A times C, whole thing over 2A. So just use, I would just use the this thing calculator, right? So if you put 26,000 here, right, and then here you put in like negative 735, and here you can put like negative 3142.5, right? And then ask them to calculate it for you. They magically calculate things for you. And I get X is equal to two numbers, right? X is equal to 0.362 or negative 0.333. So which one you want to pick? You want to pick the positive one, okay? So x is equal to 0.362 meters is how much it would depress or stretch it out, okay? So voila. All right. Any questions? Good. All right. Then let's take a look at next one. All right. So for this one, we have a mass M is attached to the end of a spring with constant K, right? So this value has a K value, constant K value. Let's use a different color. Right? It's shown. So this is mass M. Mass is given an initial displacement of x naught. So let's say this is the equilibrium position. Let's say this is where x is equal to 0, which is the equilibrium position. And it is stretched to x naught. And at this point, it has initial or velocity of v naught at this point. Okay? Ignoring friction, what would the velocity be at maximum speed? Maximum speed will only happen at the equilibrium position. This would be the V max. Because at the endpoints, it's going to come to stop. So there's no velocity at the endpoints. It'll be the maximum stretch or maximum compression, and the velocity is 0. So you're going to get maximum potential energy of spring at the endpoints, but 0 kinetic energy. Or at the equilibrium position, you're going to have the maximum kinetic energy, but no potential energy spring, so you're going to get the maximum speed at the equilibrium point. All right? So we can consider this to be our initial condition, and we could consider this to be our final condition. Okay? And since there's no friction involved, we can say, okay, since work done by friction is equal to 0, right? Therefore, total energy initial is equal to total energy final. Okay? So, total energy initial is equal to total energy final. Total energy initial, I have kinetic energy initial plus somewhat of potential energy of spring initial. I have no height change, so my potential energy of gravitation is not really required. That is equal to, right? Here I have just kinetic energy at the equilibrium point, okay? Therefore, here I have kinetic energy is equal to 1/2 mv initial, which is just v naught squared, plus 1/2 k x naught squared is my initial position of stretch. That is equal to just 1/2 mv max squared, because the maximum potential or maximum speed happens at the equilibrium position. Therefore, notice how I can cancel out the 1/2, which is very convenient. I cannot cancel out the mass because I don't have mass in this term. All right. However, I can divide both sides by mass. Right? If I divide both sides by mass, here it gets canceled out to 1, but here this cancels out to 1, and I only have v naught squared plus kx naught squared over m is equal to my v max squared. So my v max is equal to square root of, right, v naught squared plus kx naught squared over m. Voila. Okay, so that was part A. What about part B? The maximum stretch, right? The maximum stretch from the equilibrium in terms given quantities. So now they want to know how much is going to stretch, okay? And that's same as how much is going to compress too. It doesn't really matter whether it's compressed or stretched. It's going to be the same amount, whether it's this way or this way, right? That really shouldn't matter too much. Well, this is the total energy that I start with, right? So this is total energy that I start with. So I can say that total energy here has to equal to, instead of final kinetic energy, I could say final potential energy of the spring. All right, so here, let's say it's the maximum compression, or that would be the same value as maximum stretch, right? Then this to this is my X max. At X max, I have no kinetic energy, I have no potential energy of gravitation, I only have potential energy of spring at this X max. So for part B, total energy initial is equal to total energy final again. And total energy initial is the same thing that I start with, which is kinetic energy initial plus potential energy of spring initial. That has to equal to, instead of now kinetic energy final, I say potential energy of spring final. Okay? So, kinetic energy initial, again, is equal to 1/2 mv naught squared plus potential energy of spring, 1/2 kx naught squared, is equal to 1/2 kx max squared. Therefore, again, I can cancel out my 1/2s and divide both sides by k. So this will cancel out to 1. Right? This will cancel out to 1. And this will also cancel out to 1. So here I have m v naught squared over k plus x naught squared is equal to my x max squared. So if I square root both sides, I get my x max is equal to square root of, right, this mess, which is x naught squared plus mv naught squared over k. All right. All right. Any questions on this? Okay, good. Now let's take a look at this last page. Huh? All right, let's take a look at 28. So the elevator cable breaks. That's not a good thing. An elevator cable breaks when 900 kilogram elevator is 30 meters above a huge spring. Okay, so let's draw an elevator. So here's an elevator. And the cable snaps, right? Cable snaps. Now, this thing's going to fall. However, at the bottom of the elevator shaft, there's a huge spring at the bottom of the shaft. So when the elevator is 30 meters above the spring, right, it's going to basically snap. So what happens? Well, it's going to obviously fall. Right? The elevator is going to fall towards the ground, right? And when the elevator reaches to the top of the spring hasn't really been compressed yet. Okay? Then they want to know how fast it's moving right before it touches the spring. Then, for the other part, now the elevator compresses the spring, right? And comes to a stop. This much of compression is basically what the compression of x is. So this is x. Okay? Now, here, if I were to, maybe I should have made this into a different color so you can see the difference. Instead of saying initial and final, what I'm going to do is I'm going to say position 1 position 2, and position 3. Okay? So we don't have to worry about initials and finals. We just say position 1, position 2, and position 3. Now, the spring constant K, right? The K value is huge. It is like 400,000 newtons per meter. Okay? All right, so that's pretty big. That's 400,000 newtons per meter is K value. All right. So now we can actually start working on this. Now they're saying, okay, A, what work done by gravity on this elevator, there should be is, I guess, so what work is done by gravity on the elevator before it hits the spring? So they want to know how much work is done by gravity, and that is just Fg dot y, right? Right before it hits the spring. So they only want to know from here to here. So y is 30. And since Fg is down, right? Fg is downwards. And since my delta y is also down, which is right, the angle between them is 0 degrees. So here I have mg times y times cosine of 0 degrees. Therefore, here my mg, which is 900 times y, which is 30 times cosine of 0 degrees is just 1. So, what is that equal to? I forgot 9.8, sorry. Right? So, what is that equal to? That is 900 times 9.8 times 30 times 1. And if you work that out, I think you should get something like 264,600 joules is what you have. Okay? So what about part B? What is the speed of the elevator just before it strikes the spring? So for part B, they want to know what the V at point 2 is. They want to know what V at point 2 is equal to. So we're going to consider total energy at 1 is equal to total energy at 2. Right? Initial, final. Total energy at 1, I only have just potential energy gravitation at position 1. So total energy at 2, I only have kinetic energy at 2. Because I'm going to consider this to be my 0. Okay? And if I consider this to be my 0 at 2, then my height is only 30. Okay? So here, mgy1 is equal to 1 half mv at 2 squared. Okay? So you can cancel out the masses. So you get 9.8 times here, you get 30 is equal to 1 half times v2 squared. So what is 9.8 times 30 times 2? So you're going to get square root of 588 as my v2, which is 24.2487 meters per second. All right. That's how fast the elevator will be moving at position 2. Now at position 3. For part C, they want to know the amount of spring compressed. Okay, the amount of spring compressed. So for part C, they want to know how much this position of X is compressed, or spring is compressed, right? So I'm going to consider this to be my 0 now. So this is Y3 is equal to 0. Right? So in this case, my total energy at 1 is equal to my total energy at 3. Total energy at 1 is just simply potential energy gravitation. Right? However, this is the new height for my H3. Okay? Here, I only have potential energy of spring at 3. So here, I have potential energy of spring, right, at 3. You could have compared these two as well, right? You could have said total energy 2 is equal to total energy at 3. But don't forget this little potential energy gravitation at 2, if this is your new 0. Okay, maybe we could do that, solve that later, and compare the answers. So for now, I'm going to just compare these two, 1 and 3. Here I have mg, right, h3 is equal to 1/2 kx squared. H3 is 30 plus x. Okay, so mass, well, mg 30 plus x is equal to 1/2 kx squared. So let's put in the values. So again, 900 times 9.8 times 30 plus x is equal to 1/2 times 400,000 times x squared. So here I have 900 times 9.8. So I have times 30. I have 264,600 plus 8,820 x is equal to 200,000 x squared. So if I solve for x now, this looks like a quadratic equation. I'm going to bring these to the other side. So 0 is equal to 200,000 x squared, right, minus 8,820x minus 264,600. So if you were to, again, use the quadratic formula equation, just look it up on, right? So if you plug in like 200,000 for this, right? And then plug in 8,820 20 for this. And then for this one, you plug in 264,600. And you'd say, calculate. And magically, you'll get two answers, where x is equal to 1.17, right? And I guess 248, or negative 1.12838. Obviously, you're going to pick the positive value for this, right? So the x is equal to 1.17 meters. That's how much it will compress. All right. All right. So, alternative method, if you were to consider, let's say, instead of considering 1 and 3, we could have considered doing total energy at 2 is equal to total energy at 3. I'll just set it up for you so you guys can see what I'm talking about. Here, at 2, I have kinetic energy traveling at this speed. Right? Plus, I still have this tiny potential energy because I still have this is my 0. So my potential energy gravitation at 2, and that has to equal to my total energy at 3, which is just potential energy of spring at 3. Here, the kinetic energy, 1/2 mv2 squared, which is this value right here, plus potential energy gravitation is mgx. That's the height, is equal to 1/2 kx squared. So if you plug in the values, you get 1/2 times 900 times this, which is 24.2487 whatever squared, plus 900 times 9.8x is equal to 1/2 times 400,000 x squared. And if you work it out, if you work this out, let's see what you get. You get 0.5 times 900 times 24.2487 squared, and I get very, very similar to this number right here. Right? So this is actually 264,600, right? Plus, this would be 900 times 9.8, and I get exact same value as this, which is 8820x, is equal to 200,000 x squared. So you get the exact same quadratic formula, basically. 200,000 x squared minus 8820x minus 264,600, and you get exactly the same values. So it works either way. Okay? Just to show you that physics does work, even on Fridays. All right. Any questions? All right, so I'll leave this up here for a little bit so you guys can have a chance to copy it down, okay? And then as I pause this, for those of you who already finished copying down, I guess we could take a 5-minute break, right? And then come back. All right, welcome back, everybody. Let's take a look at what we're going to do for the rest of the period. If you can go to your Schoology, okay, And then if you could get to chapter 6, go to the current unit, right? Chapter 6, work and energy. If you go to chapter 6 test folder, there are two. There are two files here. This one and this one. Okay, so make sure you print out both. So this one here, print this out. And these are the formulas. If you want to use it, you can definitely use those formulas. Okay. And if you want to work on that first, then after that's completed, if you can open this one up. Now this one's challenging now. If you remember the practice problem that we did, okay, so you could see, now this one has spring in it, okay. This is very similar to what we did in the example problem in your notes packet. But your notes packet had an example problem without friction. But there's definitely friction underneath the spring right here. Okay? So friction only happens only when spring is compressed and then stretched to the equilibrium position. Alright? So this is the only part where there's friction. So keep that in mind. And mu sub k is 0.37. All right. If there are no questions, good luck. Get to work. All right. I'll stop the recording here.